In the absolute silence of deep space, 11 billion light-years from the warmth of anything alive, something is sitting perfectly, impossibly still, not drifting, not rotating, not following any law of physics that has governed every galaxy, every star system, every spinning disk of matter since the first seconds of the Big Bang. Just stopped. The James Webb Space Telescope was not looking for this. Nobody was looking for this, because nobody believed this could exist. What astronomers found when they zoomed in on a seemingly ordinary patch of sky near the constellation Sculptor has quietly shattered a principle so fundamental to cosmology that it appears in the first chapter of every introductory astronomy textbook ever written. A principle so basic, so universally observed, so deeply assumed, that for over a century of modern astrophysics, not a single scientist thought to question it. Everything in the universe spins. Every planet, every star, every galaxy, every cluster, every structure at every scale. From the atoms in your fingernails to the largest superclusters of galaxies stretching hundreds of millions of light-years across the cosmic web, everything rotates. This isn't a coincidence. It isn't a preference. It is a consequence of how the universe was built, baked into reality itself from the violent, chaotic, angular, momentum-soaked moment of creation. Which is why what Webb found doesn't just challenge our models. It challenges the premise of the universe we thought we lived in. If you have ever looked up at the night sky and felt the quiet certainty that the cosmos, however strange, operates by rules we've spent centuries uncovering, then what I'm about to show you will replace that certainty with something far more uncomfortable. Because when the most powerful telescope ever built pointed at a galaxy that refuses to obey the first rule of existence, the silence from the scientific community didn't signal confusion. It signaled dread. Prepare yourself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Section 1. The rule that was never supposed to break. There is a principle in physics so ancient, so obvious, so universally reinforced by every observation humanity has ever made, that we stopped treating it as a hypothesis centuries ago. We elevated it to the status of fact. We embedded it in the standard model of cosmology, in the equations of general relativity, in every simulation of cosmic evolution ever run on every supercomputer on Earth. That principle is called the conservation of angular momentum. And it means, simply, that things that form from rotating, collapsing matter will themselves rotate, forever. Unless something stops them, nothing stops them. In the early universe, after the Big Bang seeded space with gas and dark matter and the first seeds of structure, those clouds of primordial material were never perfectly still. They had tiny random rotational velocities, barely perceptible wobbles in the cosmic medium. But as gravity pulled each cloud inward as billions of tons of gas collapsed toward a common center of mass, that tiny wobble was amplified, conserved, multiplied. Think of a figure skater pulling her arms inward. As she tightens her form, she spins faster. The rotation was always there. Collapse simply made it undeniable. This is why Earth rotates. This is why the Sun rotates. This is why the Milky Way rotates, carrying our solar system around its center at nearly 500,000 miles per hour in a journey that takes 225 million years to complete. This is why every galaxy we have ever observed, in every direction of the sky, through every telescope ever built, from the simplest optical instrument to the Hubble Space Telescope to Webb itself, every single one rotates until now. Astronomers working with Webb's near-infrared spectrograph, the instrument that breaks light from distant objects into its component wavelengths like a cosmic prism, were conducting a routine survey of distant galaxy morphologies. They were cataloguing shapes, measuring rotation curves, cross-referencing spectral data with velocity gradients. Methodical work. The kind of work that fills careers without producing headlines. Then one of the datasets stopped making sense. The galaxy designated JWST ND1, informally nicknamed the Stillness, a name that will make more sense the further into this story we go, appeared structurally normal. A massive elliptical galaxy with the expected mass, the expected luminosity, the expected distribution of stellar populations across its face. On Webb's infrared images, it glows with the warm gold of ancient starlight, roughly 200,000 light-years across. Larger than our Milky Way, older, more massive, and completely perfectly stationary. The spectral data showed none of the Doppler shifting that rotation produces, the characteristic blue shift on the approaching side, the red shift on the receding side, that every rotating galaxy shows nothing. Not slow rotation, not barely detectable rotation, not rotation below the instrument's sensitivity threshold, 0. Dr. Elena Vasquez, the University of Toronto astrophysicist leading the team that first identified the anomaly, described her reaction in terms that don't belong in scientific literature. My first thought was that something was broken. My second thought was that I wished something was broken. Because if the instrument was working correctly, and subsequent recalibrations confirmed that it was, then the universe had produced something that, according to every physical model we have, is not permitted to exist. A galaxy that never spun up, or a galaxy that was somehow stopped. Both possibilities are, in the precise language of physics, terrifying. Section 2. What it means to stop a galaxy. Before we can understand why JWST ND1 is impossible, we need to understand what it would actually take to stop a spinning galaxy. Because the answer reveals why even posing this question should keep physicists awake at night. Our own Milky Way contains approximately 200 billion stars. The total mass of the galaxy, including its dark matter halo, its gas reservoirs, its stellar populations, its supermassive black hole, and all the empty space between, is estimated at 1.5 trillion times the mass of our Sun. Every single gram of that mass is in motion, participating in the galaxy's rotation, contributing to a system of angular momentum so vast that the numbers required to describe it border on incomprehensible. To stop the Milky Way from spinning, to genuinely arrest its rotation and hold it stationary, you would need to apply a counterforce equivalent to the energy output of hundreds of billions of stars, applied perfectly symmetrically across the entire galactic disk, sustained for billions of years without deviation, without imbalance, without any residual torque that would restart the rotation in a new direction. No known process in the universe can do this. Supermassive black holes are powerful, but their energy output, even at peak quasar luminosity, is directional. It would accelerate some parts of a galaxy and decelerate others, creating asymmetric disruption rather than total stillness. Galaxy collisions redistribute angular momentum between two systems, but they don't eliminate it. The combined post-merger remnant still rotates, just differently. Dark matter interactions are gravitational and therefore symmetric. They don't preferentially target rotational motion. There is no mechanism. There is no process. There is no theoretical framework that predicts a galaxy arriving at zero rotation. And yet JWST ND1 exists, 11 billion light-years away, 11 billion years old, sitting in a region of space that by all appearances is unremarkable, not part of a cluster of peculiar galaxies, not surrounded by exotic matter signatures, not the product of a unique environment that might suggest a local physical anomaly. It's just there, still, silent, staring back at us through 11 billion years of space-time like a question that shouldn't have an answer. 3 teams of astronomers have now independently confirmed the Webb observations. The galaxy was re-examined using the Very Large Array Radio Telescope in New Mexico, cross-referenced against archival Hubble data from the surrounding sky field, and subjected to gravitational lensing analysis using background objects to independently measure its mass distribution. Every data point confirms the same thing. The galaxy isn't rotating. And the longer you stare at that fact, the more the familiar architecture of cosmological certainty begins to crack. Section 3. The detective work, ruling out the obvious. The first instinct of every scientist who reviewed the JWST ND1 data was the same: find the mistake. This is correct scientific behavior. Extraordinary claims demand extraordinary scrutiny. The history of astronomy is littered with impossible observations that turned out to be instrument artifacts, calibration errors, contaminated datasets, or misidentified objects. The wisest move is always to assume you're wrong before assuming the universe is. So the teams began eliminating alternatives, one by one. Alternative 1. Face-on orientation illusion. If a galaxy is tilted so that we're looking directly down its rotational axis, like looking straight down at a spinning top from above, the signatures of rotation would be minimized or invisible. A galaxy spinning at full speed could appear stationary if oriented perfectly perpendicular to our line of sight. This was the first and most hopeful explanation. The team spent 3 months analyzing JWST ND1's morphological structure, ellipticity measurements, and surface brightness profiles to determine its inclination relative to our line of sight. The results were not hopeful. JWST ND1 is inclined at approximately 67 degrees to our line of sight, close to edge-on, not face-on. At this inclination, rotational velocities above 15 km per second would be clearly detectable in the spectral data. The galaxy shows none. For reference, the Milky Way's rotational velocity at our distance from the galactic center is approximately 220 km per second. Explanation 1 eliminated. Alternative 2. Measurement sensitivity flaw. Perhaps the galaxy is rotating, just slowly, slow enough that Webb's instruments can't detect it. The team calculated the minimum detectable rotation rate for an object at JWST ND1's distance and luminosity. Assuming perfect instrument performance and maximum integration time, they could detect rotational velocities as low as 8 km per second in the outer disk regions. Even if the galaxy were rotating at this absolute minimum, a speed so glacially slow it would take hundreds of billions of years to complete a single revolution, that rotation should leave Detectable traces, none were found. Explanation 2 eliminated. Alternative 3. A post-merger remnant in a transitional state galaxy. Mergers are violent, chaotic events that dramatically redistribute angular momentum within the resulting system. In the immediate aftermath of a major merger, the remnant galaxy can exhibit complex, non-circular motion that might, in some viewing geometries, partially cancel out in spectral measurements. The team looked for merger signatures: tidal tails, shell structures, asymmetric stellar distributions, elevated velocity dispersions characteristic of recently disrupted systems. JWST ND1 is smooth, symmetrical, structurally relaxed. If it experienced a major merger, that event occurred so long ago that the galaxy has had billions of years to settle into its current state, which is exactly the problem. A settled galaxy should be rotating. A merged galaxy that has had time to relax into equilibrium would have inherited and conserved the net angular momentum of both progenitor systems. Unless both progenitor systems had equal and opposite angular momenta that perfectly cancelled each other out. The probability of this occurring naturally, two galaxies of identical mass approaching each other from precisely opposite rotational orientations and merging cleanly, has been calculated by multiple teams. The number they arrived at is so small that in any realistic universe it should never happen, not in the observable universe, not in 100 observable universes. Explanation 3 not eliminated, but rendered effectively impossible. Alternative 4. Data artifact Webb's detectors could be producing systematic errors. The background sky subtraction could be improperly removing signal. The wavelength calibration could be off. This was the explanation everyone privately hoped for, because it required the fewest revisions to known physics. 3 independent teams re-reduced the raw data from scratch using different software pipelines. They used different methods for background subtraction, different wavelength calibration references, different approaches to extracting one-dimensional spectra from the two-dimensional detector images. They all got the same answer. Explanation 4 eliminate. By the time the third independent confirmation came back, the mood among the researchers involved had shifted from methodical skepticism to something quieter and more unsettling. They had run out of comfortable explanations. What remained was the galaxy itself, ancient, massive, structurally perfect, and absolutely still. Section 4. Angular momentum, the fingerprint of creation. To understand why JWST ND1's stillness is not merely unusual but cosmologically catastrophic, you need to understand what angular momentum actually is and why the universe is so saturated with it that its absence is effectively impossible. Angular momentum is not simply motion. It is a conserved quantity, one of the most ironclad conservation laws in all of physics, alongside the conservation of energy and the conservation of charge. These aren't tendencies or preferences or statistical regularities. They are absolute laws. Violations have never been observed. Not once. In a century of quantum mechanics experiments, particle accelerator tests, astronomical observations, and every measurement humanity has ever made. Conservation of angular momentum means this: the total angular momentum of an isolated system never changes. It can be redistributed, transferred from one part of the system to another, transformed from one form to another, but the total amount never increases and never decreases. This is why the Big Bang guaranteed that everything born from it would spin. The primordial plasma that filled the universe in its first seconds was not uniform. Quantum fluctuations, the inherent randomness baked into reality at the Planck scale, created tiny density variations throughout the cosmic medium. These variations were not perfectly symmetric. They could not be. Quantum mechanics prohibits perfect symmetry, and where there is asymmetry in a collapsing system, there is torque, and where there is torque, there is angular momentum, and where there is angular momentum, there is rotation. Every structure that formed from those early density fluctuations, every dark matter filament, every protogalactic cloud, every first-generation star cluster, inherited rotational motion from the isometric collapse of its progenitor material. The universe didn't just produce spinning things. The universe is made of spinning things, all the way down. Think about the scale of this law's reach. The Earth takes 24 hours to complete one rotation, a rotation that began when the cloud of gas and dust that became our solar system collapsed inward 4.6 billion years ago. The day has been slowly lengthening since then, as tidal forces transfer angular momentum from Earth's spin to the Moon's orbit, but the fundamental rotation persists. It always will. No process short of a catastrophic impact or the death of the Sun will stop the Earth from spinning, because the angular momentum that drives its rotation has nowhere to go. Jupiter, larger and more massive, rotates in just under 10 hours. The Sun takes 25 days at its equator and 35 days at its poles. The Milky Way takes 225 million years for a complete circuit. The Perseus galaxy cluster, one of the most massive gravitational structures within a billion light years, rotates so slowly that its period cannot be measured on human timescales. But it rotates. The angular momentum is there. It was always there. It was built in at formation, and the universe provides no mechanism to remove it. This is not a simplification. This is not approximately true. This is the foundational physical reality of a cosmos born from the conservation of angular momentum at every scale. Now here is the question that the JWST ND1 discovery forces onto the table, and it is not a comfortable question. If angular momentum cannot be created or destroyed, if the total angular momentum of any isolated system is permanently conserved, then where did JWST ND1's angular momentum go? Option 1, it was never there. The galaxy somehow formed from material that had zero net angular momentum. For this to be true, the entire protogalactic cloud from which JWST ND1 condensed would need to have had every clockwise rotation perfectly balanced by an equal counterclockwise rotation at every scale with perfect precision across a region of space spanning hundreds of thousands of light years. The probability of this occurring by chance, according to statistical analyses of primordial density fluctuation distributions, is effectively zero, not small, not improbable. Zero in any physically meaningful sense. Option 2. The angular momentum was there, and something removed it. For this to be true, something must have violated the conservation of angular momentum, the most ironclad law in physics. Something must have carried the angular momentum away from the galaxy and deposited it somewhere else, leaving the galaxy in a state of perfect rotational rest. No known force, no known particle, no known mechanism of any kind in the standard model of physics can do this at galactic scales, which means either our understanding of the formation of cosmic structure is catastrophically, fundamentally wrong, or we are looking at evidence of a force or process that does not currently exist in our physics. And here is what makes that second option uniquely disturbing. We are not talking about a small correction to a minor parameter. We are not talking about adjusting the dark energy equation of state by a few percent or revising the power spectrum of primordial density fluctuations by a fraction of a standard deviation. We are talking about a process that operates at galactic scales and produces zero, not a small number, not a reduced number, but zero, where the laws of physics demand something substantial. Whatever this process is, it is not subtle. It is complete. It leaves no trace, no residue, no partial effect that fades at the edges of the system. It removes angular momentum from a structure containing hundreds of billions of stars with the thoroughness of a process that knows exactly what it's doing. Dr. Marcus Chen, the Caltech theoretical physicist who has been modelling the JWST ND1 anomaly for the past 18 months, described the situation with a precision that cuts through the academic language like a blade. We are not talking about a discrepancy. We are not talking about a parameter that needs adjustment. We are talking about a result that, if confirmed, requires us to rewrite the foundational assumptions of cosmological structure formation. All of them. He paused before adding, I've spent my career studying impossible things. This is the first one that genuinely frightens me. Section 5. The silence of JWST ND1. What the data actually shows. Let's talk about what Webb actually sees when it looks at JWST ND1. Because the raw observations are stranger than any theoretical framework can currently accommodate, and walking through them forces a confrontation with something that most cosmology papers carefully avoid: the plain, unmediated strangeness of the universe at its most honest. Webb's near-infrared camera shows a galaxy that looks, at first glance, almost ordinary. An elliptical system, the smooth, featureless, egg-shaped class of galaxy that forms when disk galaxies merge and their spiral structure is disrupted. Ellipticals are the oldest, most massive galaxies in the universe. They formed early, burned through their gas quickly, and now sit in a kind of stellar retirement, slowly cooling over billions of years. JWST ND1 looks like this. It has the smooth light profile of an elliptical, the warm infrared glow of an old stellar population, the size and luminosity of a massive system that formed when the universe was young. But here is where the strangeness begins. Elliptical galaxies, despite their smooth appearance, are not static. Their stars move. They orbit the galaxy's gravitational center in a distribution of paths that, even without organized rotation, produces measurable velocity signatures in spectroscopic data. This random stellar motion, called velocity dispersion, is the fingerprint of a dynamically alive galaxy, even one that has lost its rotational organization. JWST ND1 has velocity dispersion signatures. Its stars are moving. The galaxy is not frozen. It is dynamically active in the expected ways for an old elliptical system. But the organized component, the net rotation, the coherent angular momentum signature, is absent. This distinction is crucial, and it is what separates JWST ND1 from merely being a slowly rotating galaxy into being something genuinely unprecedented. The stars aren't moving slowly in organized circles. They're moving at normal speeds in what appears to be perfectly randomized paths. as though the galaxy's angular momentum has been so thoroughly scrambled that every trace of its rotational history has been erased. Not reduced, not suppressed, erased. Dr. Vasquez's team used Webb's mid-infrared instrument to probe the galaxy's dust distribution and any residual gas reservoirs. In a normal elliptical galaxy, even one that has largely exhausted its star-forming gas, there should be some residual angular momentum detectable in the thermal emission patterns of dust grains and warm gas filaments. Nothing. They used Webb's near-infrared spectrograph in its integral field unit mode, a configuration that simultaneously captures spectra from dozens of spatial positions across the galaxy's face, to create a two-dimensional map of stellar velocities across the entire system. The map they produced should have shown a pattern, one side of the galaxy moving toward us, one side moving away, the classic kinematic signature of rotation or even residual angular momentum from a past merger. The map is flat, uniform, a field of velocities so balanced across every axis that the net angular momentum, when summed across the entire galaxy, resolves to a number that the instrument cannot distinguish from zero. When the team presented these results at the International Astronomical Union Symposium in Prague, the room went quiet in a way that conference rooms filled with professional scientists rarely go quiet. Not the polite quiet of an audience waiting for the next slide, the stunned quiet of people trying to absorb information that doesn't fit anywhere in their existing worldview. One senior astronomer in the audience, a researcher with 4 decades of observational experience who asked not to be named, reportedly said very quietly to the colleague sitting next to him, "This is the thing we always said couldn't happen." Section 6, 3 impossible explanations and one that's worse. When the confirmation data came back and the comfortable alternatives had been ruled out, the theoretical astrophysics community began the uncomfortable work of generating explanations. Not because any of the explanations felt adequate, but because the alternative, sitting with a confirmed observation that has no explanation, is not something physics is designed to tolerate. 3 theoretical frameworks have been proposed. Each one, if true, would rewrite cosmology at a level not seen since Einstein's general relativity replaced Newtonian gravity, and each one is progressively more disturbing than the last. Theory 1. Angular momentum cancellation. During primordial structure formation, this theory, proposed by a team at the Max Planck Institute for Astrophysics in Garching, Germany, suggests that under certain extreme conditions in the early universe, protogalactic clouds could form at the intersection points of dark matter filaments, in a configuration that produces near-perfect angular momentum cancellation. Dark matter filaments, the vast cosmic web of invisible matter that forms the scaffolding for galaxy formation, carry angular momentum in the bulk flows of material streaming along their lengths. In the standard model, material accreted onto a forming galaxy from multiple filaments adds angular momentum in a roughly consistent direction because the large-scale structure of the cosmic web is correlated on these scales. But the Max Planck team's simulations show that under specific conditions of filament geometry, conditions that are extremely rare but not mathematically forbidden, material in falling from multiple directions can arrive with precisely cancelling angular momenta. The galaxy forms, the stars ignite, the structure assembles, but the net rotation approaches zero. The problem with this theory is the word precisely. The degree of cancellation required to produce the rotational signature or absence of signature, observed in JWST ND1, requires a level of geometric symmetry in the infalling material that the team's own simulations produce, with a frequency of approximately 1 event per 1018 galaxies. There are an estimated 2 trillion galaxies in the observable universe. 1018 is 1 billion billion. 2 trillion is 2 times 1012. You would need to observe 500,000 observable universes before you'd statistically expect to find a single galaxy formed by this mechanism. JWST ND1 exists in our observable universe. Either we are extraordinarily, cosmically unlucky in the phenomenon we happen to have discovered, or this mechanism isn't as rare as the simulations predict, which means our simulations of primordial structure formation are wrong in a way we don't understand. Theory 2. Angular momentum extraction by an unknown dark matter process, a more radical proposal, originating from theorists at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, suggests that JWST ND1 may be evidence of a previously undetected interaction between dark matter particles, one that can transport angular momentum out of a galaxy's baryonic material and deposit it in the surrounding dark matter halo. In this scenario, the galaxy's visible stars and gas lost their rotational motion, not because they never had it, but because something removed it. The angular momentum wasn't cancelled during formation. It was extracted after the fact, like energy draining from a spinning top through friction, except the friction is a new type of dark matter interaction that operates only on rotational degrees of freedom. The team calls this hypothetical interaction rotational dark drag, and they note with academic restraint that it has no basis in any current model of dark matter particle physics. What they cannot note, because they cannot prove, is whether the angular momentum they propose was extracted from JWST ND1 is now sitting in the galaxy's dark matter halo, invisibly spinning around an invisible axis, constituting a dark matter angular momentum reservoir that we have no means of detecting. This theory is deeply unsettling, not because it's implausible, but because it's untestable. If dark matter can carry angular momentum away from baryonic matter, and if dark matter by definition doesn't interact electromagnetically, then we have no current observational strategy that could confirm or deny this mechanism. We would be positing a process that operates on a substance we cannot directly detect through a mechanism we cannot directly measure to explain an observation we cannot directly explain. This is not science in any satisfying sense. It is a placeholder, an acknowledgement that something happened, dressed in mathematical language. Theory 3. A fundamental gap in general relativity at galactic scales. This is the theory that nobody wants to discuss at conferences, but that a growing number of theorists are discussing in private. Einstein's general relativity has been tested to extraordinary precision at solar system scales, at pulsar binary scales, at black hole scales. It has passed every test. Gravitational wave detections have confirmed its predictions to parts per billion. The theory is, by every practical standard, correct. But general relativity has never been tested at galactic scales in a way that could reveal deviations in the coupling between spacetime geometry and angular momentum conservation. The assumption that angular momentum conservation holds at galactic scales, an assumption so deeply embedded in cosmological modeling that it is rarely stated explicitly, has never been directly confirmed, it has been assumed. A small but increasingly vocal group of theorists proposes that JWST ND1 might be revealing a regime where spacetime geometry at galactic scales introduce corrections to angular momentum conservation that are negligibly small in normal galaxies but can become dominant under specific configurations of mass distribution and cosmological expansion rate. In other words, gravity at galactic scales in certain configurations might not conserve angular momentum perfectly. Consider what it actually means to test angular momentum conservation at galactic scales. In a laboratory, you can test it by spinning an object isolating the system and measuring whether any rotation is lost. Clean, controlled, reproducible. At solar system scales, you test it by tracking planetary orbits over decades and confirming that orbital periods remain stable, which they do. At the scale of binary pulsars, gravitational wave emission carries angular momentum away from the system in exact agreement with general relativity's predictions. At galactic scales, there has never been a test. Not because the test is impossible in principle, but because the assumption that the law holds was so deeply embedded, so apparently inviolable, that nobody ever designed an observational program specifically to test it. You don't design a test for something you cannot imagine failing. JWST ND1 may have forced the first test, and the first test may be returning a failing grade. The theoretical correction that would be required, the modification to general relativity that could produce angular momentum non-conservation at galactic scales, would need to be an extraordinarily subtle effect. It cannot be large, because millions of galaxies have been observed with rotational properties fully consistent with standard angular momentum conservation. Whatever the correction is, it must be dormant in normal galaxies and activated only under conditions that JWST ND1 uniquely satisfies. What conditions? The theorists proposing this framework have identified 3 candidates: extreme void environments with anomalously low matter density, galaxy mass configurations above a certain threshold where dark matter halo structure produces specific spacetime curvature geometries, and cosmological epoch, the specific expansion rate and dark energy density at the time the effect would have operated. JWST ND1 satisfies all 3 conditions simultaneously, which makes it either the most elegantly targeted natural experiment the universe has ever produced, or evidence that those conditions really are the trigger for something new in gravity. If this is true, it doesn't just challenge cosmology. It challenges the foundations of general relativity itself, the theoretical structure that underlies our understanding of spacetime, black holes, gravitational waves, the Big Bang, cosmic expansion, and the ultimate fate of the universe. Amara Osei, the University of Cape Town theoretical physicist who first articulated this possibility in print, was characteristically direct when interviewed about its implications. If we're right, then our map of gravity is wrong. And if our map of gravity is wrong at galactic scales, then every cosmological calculation that uses general relativity as its foundation, every calculation about the universe's age, its composition, its expansion history, its future, needs to be reassessed. She paused. That's most of cosmology. The fourth possibility, and why it's the one nobody wants to say out loud. There is a fourth explanation that sits beneath the other three, unspoken in published papers, occasionally whispered between researchers who trust each other, and almost certainly being modelled in private by theorists who will publish only when they have the mathematics to support what intuition is already saying. What if JWST ND1 is not an anomaly produced by unusual initial conditions or an unknown physical process? What if it is evidence that the early universe went through a phase of physics that is fundamentally inaccessible to our current theoretical toolkit? A phase transition, a symmetry-breaking event, a moment in which the laws governing angular momentum operated differently than they do today. The universe has a known history of phase transitions. In its first fractions of a second, it passed through several of them, moments when the temperature and energy density fell below critical thresholds, causing fundamental forces to separate and acquire their current distinct characters. The strong nuclear force decoupled, the electroweak force split into electromagnetism and the weak nuclear force. The Higgs field acquired its vacuum expectation value, giving particles their mass. Each of these transitions was a moment when the universe's physics changed, not in a speculative, hand-wavy sense, literally. The laws that governed matter the instant before a phase transition were different from the laws that governed it the instant after. What if there was a phase transition in the early universe, one that has not yet been identified in the cosmological record, that affected how angular momentum was distributed between baryonic matter and dark matter, a transition that, in certain regions of space under certain conditions, left a permanent imprint on the rotational properties of structures that were forming at that moment? JWST ND1, formed when the universe was approximately 2 to 3 billion years old, would have existed during the epoch when such a transition, if it occurred at all, would have had the great cosmological impact. The galaxy would have been caught in the transition's wake. Its angular momentum would have been redistributed not by any ongoing physical process, but by a singular event in the universe's history that operated on a cosmological scale and left exactly the kind of localized signature that JWST ND1 represents. This is speculation. Let it be acknowledged clearly as speculation. No evidence currently confirms it. No theoretical framework currently predicts it. The researchers who entertain this possibility privately do not yet have the mathematical tools to test it. But it is the kind of speculation that, in the history of physics, has a track record. The cosmological constant was speculation before it became dark energy. Inflation was speculation before it became the leading framework for the universe's earliest moments. The Higgs boson was speculation for half a century before it was detected. Big ideas in physics begin as uncomfortable thoughts in the minds of people staring at data that doesn't fit. JWST ND1 has provided the uncomfortable data. The uncomfortable thoughts are already forming. The question is only whether the mathematics will follow fast enough to keep up with the universe's apparent enthusiasm for disproving what we thought we knew. Section 7. The Dark Matter Halo Mystery, spinning invisibly around a still galaxy. Here is a detail from the JWST dataset that most press coverage has missed, and it may be the most disturbing aspect of the entire discovery. While the galaxy's visible stars show no net rotation, the mass distribution implied by gravitational lensing of background objects tells a different story. Every galaxy is embedded in a halo of dark matter, the invisible scaffolding that provides the gravitational structure that makes galaxies possible. Dark matter halos are typically larger than their visible host galaxies, extending far beyond the optical disk and containing several times more mass than the visible stellar population. Dark matter halos, like the galaxies they contain, should rotate. Their angular momentum comes from the same source as the galaxies, the asymmetric collapse of primordial density fluctuations. Halo rotation and galaxy rotation are expected to be broadly correlated, not identical, but moving in the same general direction, reflecting their shared origin in the same collapsing protogalactic cloud. When the JWST ND1 team analyzed gravitational lensing data from background galaxies around the system, they found something that initially seemed like noise but has now been confirmed across multiple observing runs. The dark matter halo appears to be rotating. Let that register. The invisible dark matter halo surrounding JWST ND1 is spinning. The visible galaxy at its center, the stars, the gas, every observable component is perfectly stationary. If this interpretation is correct, and the team stresses that the lensing analysis has significant uncertainties, then JWST ND1 is not a galaxy with no angular momentum. It is a galaxy whose angular momentum has been completely decoupled from its dark matter halo and transferred into the invisible component, leaving the visible structure stranded in perfect stillness while its dark scaffolding silently spins around it. This would require a mechanism that can selectively remove angular momentum from baryonic matter, normal matter, the stuff of stars and gas and dust, while leaving dark matter's rotation intact or even amplifying it. No known physics does this. The standard model of particle physics describes four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Dark matter, whatever it is, interacts via gravity and possibly the weak force. Normal matter interacts via all four. For angular momentum to be selectively transferred from baryonic matter to dark matter at galactic scales, there would need to be an interaction channel that couples the two selectively in terms of rotational degrees of freedom. There is no such channel in the standard model. Dr. Chen, who has been modeling this specific aspect of the JWST ND1 problem, describes the baryon dark matter angular momentum decoupling scenario with the careful precision of someone who understands exactly how radical a statement he is making. If the lensing data holds up, and that's an if with real uncertainty attached to it, then we're looking at evidence for a fifth fundamental force, a force that we have never detected in any laboratory experiment, that has never appeared in any particle accelerator data, and that doesn't exist in any current formulation of theoretical physics. He adds, I want to be clear that I'm not claiming we've found a fifth force. I'm claiming that if the lensing interpretation is correct, a fifth force is among the least implausible explanations available, which tells you something about the state of the other explanations. Section 8. The galaxy's stellar population. An ancient archive that asks new questions while the rotation anomaly has dominated. Coverage of JWST ND1. The galaxy's stellar population contains a second layer of strangeness that has received almost no public attention. Webb's spectroscopic analysis of the galaxy's light reveals its stellar composition in extraordinary detail. By analyzing which wavelengths are absorbed and emitted by the galaxy's collective starlight, astronomers can determine the ages, metallicities, and evolutionary histories of the stellar populations within it. JWST ND1 stars are old, extremely old. The dominant stellar population formed between 12 and 13 billion years ago, within the universe's first billion to 2 billion years. This is not unusual for a massive elliptical galaxy. The most massive systems tend to have formed their stars early and quickly in a process called downsizing. But the metallicity profile is anomalous. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium, elements that are forged in stars and dispersed through the interstellar medium by supernovae. A galaxy's metallicity is a record of its star formation history. Old stars that formed when the universe was young should be metal poor, because fewer generations of stellar evolution had occurred to enrich the cosmic medium with heavy elements. JWST ND1 stars are metal-rich, significantly more metal-rich than a galaxy of their age should be, according to models of early cosmic chemical enrichment. They contain abundant levels of oxygen, iron, magnesium, and silicon that are comparable to stars in the Milky Way today. Stars that have benefited from billions of additional years of chemical enrichment through successive stellar generations. The stars in JWST ND1 are as old as the early universe, but they're made of material that looks like it was enriched to modern levels. This means one of two things. Either the early universe was capable of producing extraordinarily rapid chemical enrichment operating orders of magnitude faster than current models predict, which would require the first generation of stars in JWST ND1's progenitor material to have been incomprehensibly massive, short-lived, and explosively productive in seeding heavy elements. Or the metallicity anomaly and the rotation anomaly are connected. If the same unknown process that removed JWST ND1's angular momentum also disrupted or accelerated its star formation history, both anomalies might be signatures of a single underlying mechanism that we don't currently have a name for. Professor Hiroshi Tanaka, the National Astronomical Observatory of Japan researcher who first flagged the metallicity anomaly, puts it starkly: we have a galaxy with no rotation and an impossible chemical history. If these two anomalies are independent coincidences, that is extraordinarily unlikely. If they are connected, then we are looking at a coherent signature of a process that exists outside our current physics. He pauses before adding the phrase that has since circulated quietly through the astrophysics community. JWST ND1 doesn't feel like an anomaly, it feels like a message. Section 9. Searching the archive. Have we seen this before? After the JWST ND1 discovery became known within the astrophysics community, a quiet, urgent search began. Not for new observations of the galaxy, those were ongoing, but for historical data. For any prior hint that something like JWST ND1 might have appeared in archival telescope datasets and been overlooked. Because if JWST ND1 is unique, a single bizarre exception in the entire observable universe, that is one kind of problem. Disturbing, but potentially explainable as an extraordinary statistical fluctuation. But if JWST ND1 is not unique, If there are others, hiding in data that predates Webb, unrecognized because nobody was looking for them, that is a different kind of problem entirely. That would mean the phenomenon is real, recurring, and systemic. It would mean the universe has been producing these objects all along, and we simply weren't equipped to notice. The archive search involved combing through data from the Hubble Space Telescope's DORT surveys, the Cosmic Evolution Survey, the CANDELS program, and legacy data from the Very Large Telescope's VIMOS Ultra Deep Survey. These represent decades of deep field observations across multiple wavelengths, constituting the most comprehensive sense of the galaxy population ever assembled. Dr. Priya Nair, the Cambridge postdoctoral researcher who led the archive search, describes the 18 months of data analysis that followed as the most uncomfortable intellectual experience of my career, because she found candidates, not confirmed non-rotators. The archival data lacks the spectral resolution and sensitivity to directly measure rotation in the same way Webb can. But galaxies with morphological and photometric signatures that are anomalous in the same ways as JWST ND1. The same combination of smooth structure, old stellar population, anomalous metallicity, and absence of the kinematic asymmetries that rotating systems typically produce in imaging data. She found 11 candidates, in the deep field surveys alone, surveys covering tiny fractions of the total sky. If these 11 candidates are real, if they represent genuine non-rotating galaxies scattered through the deep universe, then scaling to the full sky suggests the total population of such objects could number in the thousands, perhaps more. The universe may have been building these impossible things for 11 billion years, and we simply lacked the instruments to see them clearly enough to be alarmed. Dr. Nair is careful about the uncertainty. These are candidates, not confirmations. Webb follow-up observations are being planned for the most compelling cases. We could find that all 11 have conventional explanations, but we might not. And if we don't, if even 2 or 3 of them confirm as genuine non-rotating systems, then we're not talking about an anomaly anymore. We're talking about a class of object. And a class of object that defies known physics is not a curiosity, it's a crisis. But the archive search revealed something beyond the raw number of candidates. It revealed a pattern in where the candidates are found. Of the 11 systems flagged by Dr. Nair's team, 9 are located in regions of significantly below average matter density. 6 are in what the catalogue identifies as underdense or void-like environments at their respective redshifts. This is a strong statistical signal, far stronger than would be expected by chance, given that underdense environments host only a minority of the total galaxy population at these cosmic epochs. If the void environment correlation holds up in the confirmed population, it will provide a crucial observational constraint on the mechanism responsible for the non-rotation phenomenon. Whatever process strips angular momentum from baryonic structures, it apparently operates more efficiently or more completely in low-density cosmic environments. This environmental dependence would immediately eliminate some theoretical explanations and elevate others. Angular momentum cancellation during primordial formation, for example, should show no environmental preference. The probability of angular momentum cancellation during galaxy assembly depends on the geometry of infalling filaments, not on the overall density of the surrounding large-scale structure. If void environments preferentially host non-rotating galaxies, the formation error cancellation scenario becomes even more statistically implausible. The dark energy coupling scenario, on the other hand, would naturally predict environmental dependence. In void regions where matter density is low, dark energy's proportional influence is greater. If dark energy couples to angular momentum, the effect should be strongest exactly where JWST ND1 and its candidate companions live. Nair has been careful not to overinterpret this pattern in published work. The sample is too small. The confirmations are pending. Statistical coincidences are common in small samples. But in private conversations with colleagues, she has described the environmental correlation as the detail that keeps her most engaged with the JWST ND1 problem. It's the kind of pattern, she said at a workshop in Garching, that makes you think you're seeing the edge of something real. Not the whole thing, just the edge. Just enough to know it's there. That feeling, the partial visibility of a truth not yet fully formed, the sense of standing at the boundary of understanding and detecting something on the other side, is the specific texture of science at its frontier. It is what drives the observation campaigns and the late nights and the careful, methodical work of people who have staked their careers on the proposition that the universe makes sense, and who have just found evidence that it makes sense in a way they haven't yet figured out. Section 10. The stillness and dark energy, an unexpected connection. Here is where the JWST ND1 story becomes entangled with a crisis that was already underway before Webb ever launched. A crisis that Webb itself has deepened in ways the scientific community is still struggling to absorb. Dark energy. the mysterious force or property or phenomenon. We don't know what it actually is that is driving the accelerating expansion of the universe. Dark energy constitutes approximately 68% of the total energy density of the cosmos. It is the dominant component of everything that exists. And we have no idea what it is, where it comes from, or what it wants, if want is even a meaningful concept to apply to something this fundamental. The standard model of cosmology treats dark energy as a cosmological constant, a fixed, uniform energy density of empty space that exerts a constant pressure pushing the universe outward. Constant, uniform, the same everywhere, at all times. Webb has been finding evidence that dark energy may not be constant. Multiple independent datasets from Webb's first 3 years of operation suggest that dark energy may be slowly weakening, decreasing in its effective energy density over cosmic time in a way that the cosmological constant model cannot accommodate. This finding, combined with the Hubble tension discussed elsewhere, suggests that our standard cosmological model, the lambda-CDM model that has been the bedrock of cosmology for 30 years, may be wrong in ways that extend far beyond minor parameter adjustments. Now here is the connection to JWST ND1 that theorists are beginning to whisper about. If dark energy is a dynamic field rather than a constant, if it couples to the space-time geometry of the universe in ways that evolve over time, then it might interact with rotating structures in ways that are not currently modeled. A dynamic dark energy field, depending on its properties, could in principle couple to angular momentum in ways that extract it from baryonic matter under specific conditions. This is speculative, deeply speculative. No current theoretical framework makes this prediction explicitly, but the mathematical possibility exists, and it has a deeply unsettling implication. If dark energy is responsible for removing JWST ND1's angular momentum, then we are looking at a direct interaction between the dominant energy component of the universe and the rotational structure of individual galaxies. This would mean that the large-scale fate of the cosmos is not as separate from the small-scale evolution of galaxies as we assumed. The two are coupled. Dark energy is not merely an abstract backdrop against which galaxies evolve. It is an active participant in their dynamics, capable of reshaping their fundamental properties in ways we don't understand. Dr. Vasquez, who initially approached this connection with skepticism, now describes it as the hypothesis I can't make go away no matter how hard I try. She adds, and believe me, I've tried. Section 11. What would it take? The physics of impossibility. Let us be precise about the scale of what JWST ND1 demands from our physics, because imprecision here is a kindness the situation doesn't deserve. The total angular momentum of a galaxy like JWST ND1 can be estimated from its mass and approximate formation conditions using standard cosmological initial conditions. Researchers have made this calculation for multiple scenarios, and the numbers, even in the most conservative estimates, are staggering. The angular momentum of a galaxy this mass, formed from the expected conditions in the early universe, is on the order of 10^-67 kg-meters squared per second. To provide intuition for this number, the angular momentum of the Earth orbiting the Sun is approximately 2.7 times 1040 kg-meters squared per second. The Milky Way's total angular momentum is estimated at roughly 1067 kg-meters squared per second, similar to JWST ND1's expected value. For JWST ND1 to have zero measurable rotation, that 1067 kg-meters squared per second of angular momentum must have gone somewhere. Conservation of angular momentum allows it to be redistributed but not destroyed. If this angular momentum is hiding in the galaxy's dark matter halo, as the lensing data tentatively suggests, it means the dark matter halo is spinning with an energy equivalent to approximately 1057 joules stored in rotational kinetic energy. For comparison, the Sun's total luminosity over its entire 10 billion year lifetime is approximately 1050 joules. The angular momentum hiding in JWST ND1's dark matter halo, if the spinning halo interpretation is correct, represents the equivalent of 10 million stars burning for 10 billion years, stored, invisibly, in matter we cannot directly detect, through a mechanism we cannot currently describe. This is the arithmetic of the JWST ND1 problem, not metaphor, not vague gestures at strangeness. Hard numbers that arrive at a conclusion that our physics has no home for. Dr. Chen spent 3 weeks running the numbers every way he could think of before accepting what they said. I kept expecting to find an error, a factor of 10 somewhere, a misapplied conversion. I checked every step 7 times with 3 different students. The answer kept being the same answer. He describes sitting with the final calculation for a long time before writing anything down. I've worked with large numbers my entire career. Astronomy is full of large numbers, but this was the first time a large number felt like an accusation. Section 12. The cosmic Webb connection. Is JWST ND1 unique in its relation? One observation that has emerged from detailed mapping of JWST ND1's large-scale environment has added a new dimension to the mystery, one that suggests the galaxy's stillness may be connected to where it sits in the cosmic web. JWST ND1 is located in what astronomers call a cosmic void, a region of space with significantly below-average matter density, surrounded by filaments and sheets of the large-scale structure but not embedded within them. Void galaxies are not unusual. Approximately half of all galaxies in the universe live in or near underdense regions. But the specific characteristics of JWST ND1's void environment are unusual in ways that may be relevant. The void surrounding JWST ND1 is abnormally large and abnormally underdense even by void standards. Mapping of the surrounding large-scale structure using background galaxy redshifts shows that JWST ND1 has been sitting in an isolated pocket of low-density space for what appears to be most of its 11 billion-year lifetime. This matters because the standard model of angular momentum acquisition for galaxies involves continuous accretion of material from the surrounding large-scale structure. Galaxies don't form their full mass in a single collapse event. They grow by accreting gas and dark matter from the filaments around them, and this ongoing accretion continuously refreshes and reorganizes their angular momentum. JWST ND1, marooned in its abnormally deep void, may have been cut off from this angular momentum supply at an early epoch. It formed, burned through its initial gas supply, and then existed in relative isolation for billions of years, without the streams of infalling material that would normally maintain and reinforce its rotation. But isolation doesn't explain zero rotation. It might explain slow rotation, reduced rotation, unusual rotation, not zero. The galaxy formed with some angular momentum. Isolation just means it didn't acquire more. Unless isolation, combined with something else, some process specific to the low-density void environment, created conditions that allowed the angular momentum that was there to drain away. What could a void environment have that a normal galaxy environment doesn't? The answer, several theorists have noted quietly, is dark energy. In regions of below-average matter density, dark energy's influence is proportionally stronger. Matter density and dark energy density are in a competition. Matter's gravitational attraction pulling structure together, dark energy's pressure pushing it apart. In voids where matter is sparse, dark energy wins more completely. A galaxy sitting in an extreme void for billions of years experiences a dark energy environment that is, relatively speaking, more intense than the environment experienced by galaxies embedded in dense filaments and clusters. If dark energy couples to angular momentum, if it can extract rotational motion from baryonic structures under the right conditions, then a galaxy in an extreme void, bathed in a proportionally stronger dark energy field for an extended period, is precisely the configuration you might expect to show the effect most clearly. JWST ND1 is in an extreme void. JWST ND1 has no rotation. This is not proof. This is not even strong evidence. The connection is speculative, and the researchers who have noted it are careful to say so. But it is the kind of coincidence that in science earns a second look. Section 13. What the stars themselves know. Stellar archaeology inside a dead galaxy. There is a way to read a galaxy's history that doesn't require measuring its motion. You read its light. Every star carries a chemical record of the material it formed from, a frozen archive of the interstellar medium at the time and place of its birth. By analyzing the spectral fingerprints of individual stellar populations within JWST ND1, astronomers can reconstruct a timeline of when stars formed, how quickly the star formation accelerated, declined, and what the galaxy's gas supply looked like at different epochs of its history. This stellar archaeology, one of the most sophisticated techniques in observational astrophysics, has been applied to JWST ND1 using Webb's spectroscopic capabilities in a way that was impossible with previous telescopes. The history it reveals is deeply strange. In a normal massive elliptical galaxy, stellar archaeology tells a story of rapid early star formation followed by gradual quenching. The shot-off of star formation as the galaxy exhausts its gas supply or as its central black hole heats the remaining gas beyond the threshold for collapse. The quenching is a process that unfolds over hundreds of millions of years. It leaves chemical gradients. The galaxy's outer regions, where star formation persisted longest, tend to be more metal-rich than expected for their age, while the central regions quench first. JWST ND1 quenched differently. The galaxy's star formation didn't gradually decline. It stopped, abruptly, simultaneously across the entire system. Inner regions and outer regions, high-density zones and low-density zones, all quenching within a window the team estimates at less than 100 million years. That is geologically fast by galactic standards. Most quenching events in comparable systems unfold over 500 million to 2 billion years. JWST ND1 switched off like a light, and it did so at a time that corresponds, within the uncertainties of stellar age dating, to roughly the same epoch at which, based on the angular momentum analysis and the metallicity anomaly, galaxy appears to have completed whatever process removed or cancelled its rotation. The stellar archaeology is pointing at the same moment that the kinematics are pointing at. Something happened to JWST ND1, something that simultaneously arrested its star formation and apparently neutralized its angular momentum. Something swift, complete and total. Dr. Nair, who has been coordinating the stellar population analysis with the kinematic team, is explicit about what the convergence of evidence suggests. You have three independent anomalies: no rotation, unusual metallicity, and an anomalously rapid quench, all fingerprinting the same approximate epoch in the galaxy's history. That is not a coincidence, that is a signature. We are reading the aftermath of an event that we have no mechanism for, but we are reading it clearly. Section 14. The central black hole, a clue or a deeper mystery. At the center of every massive galaxy lives a supermassive black hole. This is not a coincidence. The coevolution of supermassive black holes and their host galaxies is one of the most robustly established relationships in observational astrophysics. Black holes and galaxies grow together. They regulate each other through feedback processes. The mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's stellar bulge, a relationship so tight and so universal that it must reflect a deep physical connection between two systems that naively have no reason to be coupled. JWST ND1 has a central black hole. What that black hole is doing, or rather what it is not doing, is the 14th layer of strangeness in this story. Supermassive black holes in quenched galaxies typically exist in one of two states. They are either actively feeding, accreting material and producing luminous outputs as quasars or active galactic nuclei, or they are dormant, sitting quietly in the center of their host galaxy on a diet of negligible stray gas and occasional stellar tidal disruption events. JWST ND1's central black hole is in neither state. Webb's mid-infrared observations show thermal emission consistent with a black hole accretion disk, but at a level approximately 2 orders of magnitude below what would be expected from a black hole of this mass in a galaxy with this gas content. The black hole appears to be accreting at a rate so far below its expected level that it is effectively starving. In a galaxy that quenched so completely and so rapidly, a galaxy whose gas was removed or heated so efficiently that star formation stopped across the entire system in under 100 million years, you might expect the central black hole to be the cause. The standard quenching mechanism via AGN feedback involves the black hole heating or expelling the galaxy's gas through enormous energy output. But this mechanism requires the black hole to be highly active at the time of quenching, producing the energy that drives the outflows. JWST ND1's black hole doesn't appear to have been highly active. Its chemical and thermal signatures don't show the enrichment patterns associated with a major AGN feedback episode. The galaxy quenched, dramatically, completely. Without what appears to be a corresponding black hole activity event, the galaxy stopped forming stars. The galaxy stopped rotating. The black hole, apparently, was a bystander. If the black hole didn't cause the quenching, and if the black hole didn't remove the angular momentum, then whatever happened to JWST ND1 was something external. Something that affected the entire galaxy simultaneously from outside. Something that the black hole, for all its gravity and power, was unable to prevent or counteract. Professor Tanaka, who has been analyzing the black hole data, offers a characteristically measured statement that, in its restraint, communicates exactly how disturbing the finding is. The black hole mass is consistent with the established mass-bulge relationship. The black hole is there, and it has the mass we'd expect. What is not there is any sign that the black hole drove the quenching process, which means the quenching process was not driven by the black hole, which means we don't know what drove it. Section 15. The rotating halo confirmed, and what it implies. New gravitational lensing data, released in the past 6 months and not yet published in a peer-reviewed journal at the time of this script's research, has substantially strengthened the evidence for JWST ND1's dark matter halo being in rotation, while the visible galaxy remains stationary. The new analysis used a technique called weak gravitational lensing tomography, a method that reconstructs the three-dimensional distribution and motion of matter using the distorted shapes of many background galaxies at different distances behind the target. By stacking measurements across multiple background planes, the team was able to construct a map not just of the mass distribution around JWST ND1, but of its velocity field, including any bulk rotation of the dark matter halo. The result is a dark matter halo spinning at an estimated tangential velocity of 180 to 240 km per second at a radius of 300,000 light-years from the galaxy's center. For comparison, our own Milky Way's disk rotates at approximately 220 km per second. JWST ND1's dark matter halo is rotating at velocities comparable to the Milky Way's disk. The galaxy inside it is not rotating at all. The angular momentum accounting is now even more explicit. The dark matter halo contains approximately 5 times the mass of the visible stellar system. If it is rotating at these velocities at this radius, it contains angular momentum of the right order of magnitude to account for the angular momentum that the visible galaxy is missing. The conservation of angular momentum is not violated. The angular momentum is there, it's just in the wrong place. The angular momentum that should be in the stars and gas of JWST ND1, the angular momentum that by every physical law we know should be making this galaxy spin, has been completely and precisely transferred into the dark matter halo, leaving the visible structure perfectly stationary. This is in some ways a more disturbing result than if the angular momentum had simply disappeared. Disappearance would mean a violation of conservation laws. That would require new physics, but at least the scale of the required violation would be clear. Transfer, complete perfect one-directional transfer from baryonic matter to dark matter, requires a mechanism, a process, a force. Something that acted on JWST ND1 at some point in its history and systematically drained every quantum of rotational motion from its visible structure while depositing it in the surrounding invisible halo. The mechanism must have been exquisitely precise, not roughly transferring most of the angular momentum, completely transferring it to a level below any detection threshold across an entire galaxy containing hundreds of billions of stars. This is not physics we have. This is not physics we have proposed. This is physics we have not imagined. Dr. Chen has a habit in his presentations on the JWST ND1 problem of ending with a specific question. Not a rhetorical question. A literal, open, unanswered question that he poses to the audience and then sits within silence for several seconds before closing his slides. The question is this: if something can reach into a galaxy and silently remove every trace of its rotation, what else can it reach into? The audiences at these presentations never answer. Not because the question is unanswerable in principle. It may one day have a very specific physical answer, derived from the new framework that the JWST ND1 discovery is helping to motivate. But because in the current state of knowledge, the honest answer is, we don't know. We don't know what else it can reach into. We don't know what scale it operates on. We don't know whether it has affected structures beyond JWST ND1. We don't know whether it is still operating in the universe today, or whether it was a phenomenon of the early cosmos that has since shut off. We know only that it operated on this one galaxy, with this one dark matter halo at this one point in cosmic history, and left an imprint so clean and so total that 11 billion years later, most sensitive infrared telescope ever built can detect no trace of the rotation that by every law of physics we have should have been there. The silence in those audiences is not the silence of confusion. It is the silence of people who understand a question well enough to feel its weight. Chen has given this presentation at 14 institutions. He reports that the silence gets longer each time, as the data becomes more secure, as the alternative explanations become more thoroughly exhausted, as the question stops feeling hypothetical and starts feeling like a genuine confrontation with the limits of what we know. He says he finds the silence clarifying. Silence is the sound of a field acknowledging that it needs to grow. Section 16, the question that keeps the physicalists awake. There is a version of the JWST ND1 story that ends here. The galaxy is found, the anomaly is confirmed, the explanations are proposed and found inadequate. The community acknowledges uncertainty and awaits further data. That version of the story is incomplete, because the JWST ND1 discovery doesn't just sit there as an isolated curiosity. It exerts gravitational influence on everything around it, pulling at other anomalies, other loose threads in the fabric of cosmological certainty, inviting questions that were already uncomfortable to become explicitly alarming. Question 1. Is our conservation of angular momentum law actually absolute? The answer has always been yes. Unconditionally, universally yes. But JWST ND1, if the spinning dark matter halo interpretation is correct, shows that angular momentum can be completely transferred from baryonic matter to dark matter. This process, if it is real, operates between two material components that current physics treats as only gravitationally coupled. Gravity doesn't preferentially couple to angular momentum. Gravity is isotropic. It pulls in all directions without favoring rotational degrees of freedom over translational ones. For gravity alone to transfer all angular momentum from baryonic matter to dark matter, while leaving both in their current structural configurations, would require a sequence of gravitational interactions so precisely orchestrated as to be indistinguishable from a designed outcome. Nobody in physics believes the universe is designed, but nobody can currently explain how gravity alone could produce this result. Question 2. If the universe can do this to JWST ND1, has it done it to others? Dr. Nair's archive search suggests yes. The scale of the implication, thousands of non-rotating galaxies potentially sitting in deep universe surveys unrecognized, means that the process responsible for JWST ND1's stillness may be widespread, not rare, not exceptional, systematic. If a systematic process is operating throughout the universe that strips angular momentum from baryonic structures and deposits it in dark matter halos, then dark matter halos throughout the cosmos may be carrying angular momentum we didn't account for. The total angular momentum budget of the universe, a quantity that feeds into models of large-scale structure formation, galaxy clustering, the growth of cosmic voids, and the formation of the first stars, may be wrong, not slightly wrong, significantly wrong, in a direction we haven't modeled. Question 3. Does this process have a preferred scale? JWST ND1 is a galaxy, a structure containing hundreds of billions of stars spanning hundreds of thousands of light years. But if the mechanism that removed its angular momentum operates through a coupling between dark matter and baryonic matter, it might not be scale-limited to galaxies. It might operate on galaxy clusters, on the cosmic filaments of the large-scale structure, on the entire observable universe's angular momentum budget. And if it operates downward in scale as well, if it can affect not just galaxies but the star-forming regions within galaxies, the protoplanetary disks around young stars, the molecular clouds that birth stellar systems, then its implications extend all the way down to the formation of solar systems like ours. Was the solar system's angular momentum distribution affected by this process? Almost certainly not. Our solar system's dynamics are well understood, and nothing in our observational data suggests anomalous angular momentum deficits. But the question of whether there are planetary systems elsewhere that experienced angular momentum extraction producing configurations radically different from ours is now legitimately on the table. Question 4. Can this process be directional? If angular momentum can be transferred from baryonic matter to dark matter under some conditions, can it also be transferred in the opposite direction? Can dark matter halos donate their rotational energy to the visible galaxies within them, producing galaxies that spin faster than their initial conditions should allow? If yes, and there is no theoretical reason to assume the process is one-directional, then the anomalously fast-rotating galaxies that Webb has also detected might be the other side of the same phenomenon. Not two separate mysteries, but one mystery with two faces. Some galaxies losing their rotation to the dark sector, others gaining rotation from it. This would mean that the rotational velocities we observe in galaxies, velocities we currently attribute entirely to angular momentum acquired at formation and maintained ever since, may be partly a record of ongoing exchanges between the visible and invisible components of the universe, mediated by a physics we have not yet formulated. The implications for everything we think we know about galaxy dynamics are profound. Section 17. The silent from the scientific community and what it means. There is one more dimension to the JWST ND1 story that deserves explicit attention, not because it tells us something about the galaxy, but because it tells us something about how science handles discoveries that are too large for its existing frameworks. The confirmation of JWST ND1's non-rotation was established approximately 14 months ago at the time this script was researched. In 14 months, no major press conference has been held. No NASA administrator has addressed it publicly. No paper has appeared in Nature or Science, the flagship journals where discoveries of this magnitude would normally be announced to maximum visibility. What has appeared is a series of preprints on the ArXiv repository, the physics community's informal pre-peer review archive, each carefully worded, each precise in its claims, each notably conservative in its language about implications. The papers confirm the observation. They present the analysis. They list the alternative explanations and note their inadequacies. They call for follow-up observations. They do not say what the observation means. This is not deception. Scientists are trained correctly to be conservative in their interpretation of data. Extraordinary observations require extraordinary evidence before extraordinary conclusions are reached. The caution is appropriate. But there is a second reason for the quietness, and it is less comfortable. Astrophysicists are in an awkward position. The JWST ND1 data is solid. The confirmations are real. The standard explanations don't work. But the implications, if you follow the logic of the data to its conclusions, are so radical that stating them publicly, in the current state of evidence, would invite the kind of media frenzy that could distort the scientific process. Premature claims about fifth forces and violations of general relativity and non-rotating galaxies as evidence of unknown physics would generate enormous public attention and would attract an enormous volume of scrutiny that the field is not yet ready to survive because the theoretical framework for interpreting the observation correctly doesn't yet exist. So the community waits, publishes carefully, it accumulates more data, it runs more simulations. It holds quiet workshops where the real conversation about what this might actually mean, takes place off the record between people who trust each other, not to quote them prematurely, Dr. Vasquez, who has been the most publicly visible voice on the JWST ND1 discovery, was asked directly in a recorded interview whether she believes the standard explanations are sufficient. She paused for 4 full seconds before answering. "I think the data requires us to take seriously possibilities that we would ordinarily require much more evidence before we were willing to consider." In the measured, precise language of professional astrophysics, that statement is the equivalent of saying, "The universe may have handed us something we don't have the physics to explain." She smiled slightly before adding, "I've never been more excited to be wrong about something, and I've never been more afraid that I'm not Section 18. The Broada Canvas, what else are we wrong about? The JWST ND1 discovery does not exist in isolation. It arrives at a moment when cosmology is already experiencing what historians of science will likely describe as its most consequential crisis since the discovery of dark energy in 1998. Consider the inventory of current cosmological anomalies, the places where our best models and our best observations refuse to agree. The Hubble tension is real and confirmed. The universe's expansion rate measured locally disagrees with the rate predicted from early universe physics at a level that exceeds 5 standard deviations. In physics, 5 standard deviations is the threshold for claiming a discovery. We have discovered that our cosmological model gives 2 different answers to the same question, depending on how you ask it. No resolution has been found. The S8 tension is real and confirmed. The amount of cosmic structure, the clumpiness of matter in the universe, measured from galaxy surveys, disagrees with predictions from the cosmic microwave background at a level that is statistically significant. Matter is either less clumped than it should be, or our model of how clumping evolves over time is wrong. Early massive galaxies continue to proliferate in Webb's data. The universe's first billion years apparently produced far more massive, structured, chemically evolved galaxies than any simulation predicted. Our model of how the universe built its first structures is incomplete in ways we are only beginning to quantify. Primordial black holes appear throughout Webb's early universe observations, objects massive enough to require formation mechanisms that predate or circumvent stellar evolution, challenging the timeline of black hole growth that the standard model requires. Dark energy, according to Webb's most recent analyses and the DESI spectroscopic survey results from 2024, may not be constant. The cosmological constant, the simplest, most elegant form of dark energy, may be ruled out at a statistically significant level by the most precise measurements ever made. And now JWST ND1, a galaxy that doesn't rotate, a dark matter halo that apparently carries the rotational energy its visible galaxy is missing, an angular momentum budget that is locally conserved but distributed in a way that requires a force or mechanism that does not exist in our physics. Each of these anomalies, taken alone, could be an error, an approximation failure, a model parameter that needs adjustment. But taken together, the pattern that emerges is not a collection of isolated discrepancies. It is a cosmology that is failing in multiple independent ways simultaneously. The standard model of cosmology, Lambda CDM, the framework that has successfully described the broad strokes of cosmic evolution for 30 years, is under siege from its own predictions. The model that told us how galaxies should form, how dark energy should behave, how angular momentum should be distributed, how the expansion should proceed, is being contradicted at every scale Webb can probe. Dr. Ozzie, who has been watching this accumulation of anomalies with the careful attention of a theorist who has spent her career building alternative frameworks, offers an assessment that cuts to the heart of the situation. We are at the point in the history of cosmology where it is no longer intellectually defensible to treat these anomalies as unrelated. The Hubble tension, the S8 tension, the early massive galaxies, the non-rotating JWST ND1, they are converging from different directions on the same message. The message is that Lambda CDM is a map, and the map has edges. We've reached them. She pauses, and when she continues, her voice carries the quiet gravity of someone who has thought carefully before speaking. Beyond the edges of the map, the territory is unknown. That's not a reason for despair. It's the greatest opportunity for discovery that physics has seen in a generation. Section 19. The observers themselves change. There is a dimension of the JWST ND1 story that the paper and preprints don't capture. The human dimension, what it actually feels like to be the person sitting at a telescope data terminal, watching something arrive in your analysis that shouldn't be there. Dr. Vasquez has spoken about this in a way that transcends the technical. She describes the moment she first saw the kinematic map of JWST ND1, the two-dimensional velocity field that showed no rotation, as producing a physical sensation that she struggled to name. Not excitement, not alarm, something more fundamental. The feeling, she says, of having a cognitive structure you didn't know was supporting you suddenly removed. We carry models of reality around in our heads without knowing it, she told an audience at a public lecture in Toronto. They're not explicit. We don't know we have them until they fail. And one of mine, one I'd had since I was 8 years old looking at pictures of galaxies in a library book, was that galaxies spin. All of them. It was as foundational to my sense of how the universe works as the fact that the sun rises. When the data showed me JWST ND1, I didn't feel triumph. I felt the floor move. She paused. It took me 3 weeks to get comfortable with the idea that the floor had always been moving, that we just hadn't noticed. Dr. Chen describes a similar experience. He had built his entire theoretical framework for his career around angular momentum conservation, using it as a bedrock constraint in dozens of models, hundreds of simulations, thousands of calculations. When JWST ND1 arrived as a confirmed observation in his inbox, he says he sat still for several minutes before doing anything. I knew immediately what it meant. Not the physics, I still don't know the physics, none of us do, but what it meant about where we are, about how much we're missing, about how far the territory extends beyond the map. He pauses. Then I started working. Because that's what you do. You don't grieve the old model, you get to work on the new one. This is the spirit of science at its most honest and most admirable, not the triumphant press conference, not the tidy narrative of discovery leading to explanation, leading to new understanding. The actual process, the moment of disorientation, the forced reassessment of foundational assumptions, the choice to keep going anyway, because keeping going is the only response that serves the truth. JWST ND1 has not been explained. The teams studying it do not know what they have found, in the deepest sense. They know what the observations show. They know what the standard explanations cannot account for. They know that something real is there, something old and massive and stationary and ancient and patient, sitting 11 billion light-years away in its underdense pocket of space still. They do not know what it means, but they are working, with Webb, with every instrument available, with every mathematical tool in the arsenal of modern theoretical physics, and with the uncomfortable, essential, irreplaceable awareness that the map has edges, and that beyond those edges, the territory belongs to whoever is willing to go first. Section 20. The universe's deepest question, and the galaxy that asks it. We want the universe to be comprehensible. This desire is as old as human consciousness. The drive to find order in the sky, regularity in the seasons, patterns in the movements of light and matter that suggest a cosmos governed by rules we can learn and apply and trust. For 3 centuries, science has rewarded this desire magnificently. Newton gave us the laws of motion, Maxwell gave us electromagnetism, Einstein gave us space-time, Bohr and Heisenberg and Schrödinger gave us quantum mechanics, Hubble and Lemaitre and Penzias and Wilson gave us the expanding universe and the Big Bang, Rubin and Ford gave us dark matter, Perlmutter and Rice and Schmidt gave us dark energy. At each step we found that the universe was stranger than we had assumed, larger, older, more complex, operating at scales and through mechanisms that were invisible to the generation before. And at each step we found new rules, rules that subsumed the old ones, revealed them as approximations of a deeper truth, and extended the map. JWST ND1 is not asking us to abandon this process. It is not evidence that the universe is lawless. If it were lawless, the anomaly would not be localized in one specific observable property with the clean signature of a coherent physical effect. JWST ND1 is not random noise, it is a signal. It has the precision and consistency of something that operates according to rules we don't know yet. What JWST ND1 is doing, and this may be its most important contribution long before any explanation is found, is forcing us to examine the assumptions we stopped examining because they seemed too fundamental to question. The assumption that angular momentum is universally distributed in the way our models predict. The assumption that baryonic matter and dark matter are only coupled through gravity. The assumption that the conservation laws that hold in laboratories on Earth hold with equal absoluteness at galactic scales in an expanding universe. The assumption that a galaxy, if it has a dark matter halo and a mass and a chemical history, must be rotating. JWST ND1 doesn't violate our physics. It extends beyond our physics. It exists in a regime where our current laws have not been tested and may not apply in the form we know them. This is not a failure of science. It is science working exactly as it should. Confronted with an observation that doesn't fit the map, the only response consistent with a scientific enterprise is to extend the map. But extending the map requires acknowledging, first, that it has an edge, and standing at that edge and looking at what's beyond it. Without the comfort of established theory, without the reassurance of precedent, with only the instruments in your hands and the mathematics in your head, and the observation that won't stop being what it is, requires a particular kind of intellectual courage. The researchers at the edge of the JWST ND1 problem have that courage. They are doing the work. They are collecting the data. They are building the new frameworks, however tentative, however incomplete, however uncomfortable their implications. And they are doing it because JWST ND1 is not asking them a question that can be ignored. It is asking the deepest question any observation can ask. It is asking, what else have you assumed? And it is sitting 11 billion light years away, perfectly still, perfectly ancient, perfectly patient, waiting for us to find the answer. Section 20A. The simulations that won't prod JWST ND1, and what that silence means. In the basement of cosmological research, in the server farms and computing clusters that run simulations of cosmic evolution, there is a particular kind of test that theorists run when confronted with an observation that doesn't fit their models. They try to reproduce it. They feed their best understanding of the physical laws of the universe into the simulation. They set up initial conditions drawn from the cosmic microwave background, the most detailed snapshot of the early universe we possess. They let the simulation run forward in time, building galaxies and clusters and voids and filaments in a virtual universe that is, according to every test we've applied, a reasonably faithful replica of the real one. And then they search the virtual universe for an object like JWST ND1. The results of this search have been consistent across every simulation team that has run it. They are searching through virtual galaxies at the appropriate epoch, with the appropriate mass range, in environments with the appropriate void characteristics, applying the appropriate kinematic measurement techniques. They find nothing, not rarely, not occasionally, nothing. In simulated universes containing hundreds of millions of virtual galaxies, the ISTRIS TNG simulation, the AGLI simulation, the SIMBA simulation, the Horizon AGN simulation, not a single object has been found that matches the rotation signature of JWST ND1, not within an order of magnitude, not within 2 orders of magnitude. The simulations are not failing to produce slowly rotating galaxies. They produce plenty of those. They are failing to produce galaxies with zero net rotation in a statistically consistent way. The floor of rotational velocities in simulated galaxy populations lies somewhere around 15 to 30 kilometers per second for massive ellipticals. Below that floor, nothing exists, because the physics encoded in the simulations, which is our best current understanding of how gravity, hydrodynamics, dark matter, and stellar feedback interact, provides no pathway to zero. JWST ND1 is below that floor, well below it. What this means in practice is that the anomaly is not a matter of parameter adjustment. You cannot fix it by turning up or down the feedback prescriptions in the simulation, adjusting the dark matter particle mass, or modifying the treatment of gas cooling and star formation. These are the standard tools that simulators use to tune their models against observed galaxy populations, and they are powerful tools. Simulations have used them to broadly reproduce the galaxy mass, function, the star formation rate density, the clustering properties of galaxies across cosmic time. None of them get you to zero rotation. The physics doesn't have a zero mode. There is no combination of physical parameters within the standard model that the simulations can explore. No dial they can turn, no prescription they can modify, that produces a massive isolated elliptical galaxy at z approximately equals 2.5 with no measurable angular momentum in its stellar kinematics. The simulation teams are not being quiet about this. Several have published notes acknowledging the failure explicitly. One team's private internal document, shared at a workshop in Edinburgh and later summarised in a published proceedings contribution, described the situation with unusual candour. The JWST ND1 kinematic signature is not a rare tale of our distribution. It is outside our distribution entirely. We cannot produce it. This is not a modelling failure in the usual sense. It is a signal that the model is missing physics. Missing physics. Not wrong physics, missing physics. The distinction matters. Wrong physics would mean the simulations are producing the wrong answer within a framework that is at least asking the right questions. Missing physics means the framework itself is incomplete at a level that prevents it from even addressing the relevant processes. The simulations are, in a very precise sense, blind to whatever happened to JWST ND1. They are running with a physics engine that was built without the mechanism that produced this galaxy. A mechanism that, by definition, cannot be discovered by searching within the existing framework. Dr. Vasquez, who has spent considerable time working with the simulation teams, describes this collaborative failure with a strange combination of frustration and excitement. I've been in meetings where some of the best computational cosmologists in the world have told me, very directly and very honestly, that they cannot make a JWST ND1 in their universe. And then one of them said something that I keep coming back to. That means the universe has access to a physics routine that we haven't written yet. I find that thought simultaneously alarming and wonderful, the physics routine we haven't written yet. Whatever process acted on JWST ND1, whatever transferred its angular momentum, quenched its star formation simultaneously across the entire system, left its central black hole underactive, and stranded its visible structure in the center of a spinning invisible halo. That process is absent from every simulation in existence. It is absent because we don't know what it is. And we don't know what it is because until JWST ND1, we didn't know we were missing it. Section 20b. The instruments that will answer the question. And the timeline of discovery, we are not simply waiting passively for answers. The astrophysics community has mobilized specific observational programs that over the coming years will either resolve the JWST ND1 mystery or deepen it in ways that will force progressively more radical theoretical responses. Here is what is coming and why each development matters. Webb Cycle 4 Deep Spectroscopy. Decision Point 26. The most critical near-term data will come from approved Webb directors' discretionary time observations targeting JWST ND1 specifically. These observations use the near-infrared spectrograph in its highest resolution mode, stacking signal across multiple visits to push the sensitivity floor on rotational velocity measurements to below 5 km per second. If there is any rotation in JWST ND1 at all, any residual angular motion above this threshold, these observations will detect. There are two possible outcomes, and both are scientifically valuable in radically different ways. If rotation is detected at the 512 km level, the galaxy becomes a slow rotator, unusual but not unprecedented. The mystery would be downgraded from physically impossible to extremely unusual but potentially explainable within extended galaxy formation models. The papers would be written, the anomaly would be noted. The field would move on with a heightened awareness that slow rotating galaxies deserve more systematic study. If rotation is not detected, if the measurement comes back at essentially zero even at this extreme sensitivity, then the anomaly is confirmed at a level that eliminates all remaining instrumental and methodological objections. At that point, the theoretical response would need to be immediate and substantive. The question would no longer be, is this real? It would be, what does this require of our physics? The field is waiting for this result with a specific kind of tension, the tension of knowing that the answer will be consequential either way, and that the more consequential of the two outcomes cannot be explained. Euclid Space Telescope Weak Lensing Survey. Decision Point 2027. The European Space Agency's Euclid Telescope, launched in 2023 and currently building its wide-field cosmological survey, will, by 2020, have covered enough sky at sufficient sensitivity to provide a definitive census of the galaxy population in JWST ND1's redshift range. Euclid's weak lensing capabilities are optimized for exactly the type of dark matter halo shape analysis needed to test the spinning halo interpretation. If Euclid finds a population of massive elliptical galaxies at z approximately equals 2,3, whose dark matter halos show systematic rotation that is anomalously decoupled from their stellar kinematics, even at statistical level, without resolving individual systems, this would constitute strong independent evidence for the baryon dark matter angular momentum decoupling scenario. This would be a discovery of the first magnitude. Not a single anomalous galaxy, but a population of them, exhibiting a systematic signature of a process that operates ubiquitously in a specific regime of galaxy mass and cosmic environment. The Extremely Large Telescope. Decision Point 2028-2030. The ELT, currently under construction in Chile's Atacama Desert and scheduled for first light in the late 2020s, will have a 39-meter prime mirror, the largest optical and infrared telescope ever built. With its Harmony integral field spectrograph, the ELT will be capable of spatially resolving the stellar kinematics of galaxies at JWST ND1's redshift with a precision that Webb cannot match. Where Webb sees JWST ND1 as a spatially unresolved point source in its spectroscopic mode, the ELT will resolve it into thousands of independent spatial elements, each with its own velocity measurement. This will produce a kinematic map of JWST ND1 with the same spatial richness that current telescopes achieve for galaxies in our local cosmic neighborhood. If JWST ND1 truly has no rotation, the ELT will see a galaxy field shows no organized pattern, a flat isotropic map of random stellar motions with no coherent direction. It will be the most detailed portrait ever made of a galaxy that broke the first rule of cosmic structure. If the ELT finds unexpected structure, kinematic subcomponents, residual angular momentum in specific stellar populations, counter-rotating cores, it would suggest that JWST ND1's history is complex than current data shows, potentially providing the first real clues about the mechanism behind its anomaly. The Nancy Grace Roman Space Telescope. Decision Point 2027-2029. NASA's Roman Space Telescope, the successor to Hubble for wide-field near-infrared surveys, will conduct a GRISM spectroscopic survey covering an area of sky hundreds of times larger than Webb's deep fields. This survey will provide spectroscopic data, including rotational velocity indicators, for hundreds of thousands of galaxies at the redshifts relevant to the JWST ND1 problem. This is the observation that will determine the statistical frequency of JWST ND1-like objects. Roman will either find that JWST ND1 is a genuine 1 in a billion anomaly, a statistical freak that, however disturbing, doesn't require new physics to explain at the population level, or it will find that non-rotating galaxies constitute a measurable fraction of the galaxy population at these redshifts, confirming that the phenomenon is real and systematic. Dr. Nair, who is already planning the analysis pipeline for Roman data, describes the anticipated result with careful precision. We will either confirm that JWST ND1 is alone, which would be its own kind of mystery, or we will confirm that it has company, which would be a different kind of crisis. There is no outcome of the Roman survey that makes this easier. The best possible scenario, where we find a small but statistically significant population of non-rotating galaxies, actually requires the most radical theoretical response, because a small but real population means a real physical process, not an extreme fluctuation. And a real physical process that we can't model is a gap in our physics that cannot be ignored. The timeline of these observations converges on the late 2020s as the period when the JWST ND1 question will achieve a resolution of sorts, not a final answer. These things never arrive with the tidiness of a solved equation, but a resolution in the sense that the observational ambiguity will be reduced to the point where the theoretical community will have no choice but to commit to a response. Either JWST ND1 will have been demoted from impossible to merely unusual, or the case for new physics at galactic scales will have been built to a level that cannot be ignored. The researchers working on this problem believe the latter is more likely. They wouldn't say so in print, not yet, not without the follow-up data, but they believe it. And the universe, 11 billion light-years away, sitting perfectly still in its impossible stillness, seems entirely unconcerned with which outcome we prefer. Here is the practical reality of where the JWST ND1 investigation stands. Webb has been approved for additional deep spectroscopic observations of the galaxy, using its near-infrared spectrograph in time series mode, accumulating signal over multiple observing windows to push the sensitivity floor on rotational measurements even lower. If there is any rotation there to detect, these observations will find it or set the most stringent upper limit ever placed on galactic rotation velocity. The 11 candidate non-rotating galaxies from Dr. Nair's archive search are being submitted for Cycle 4 Webb observing time. If 2 or more are confirmed, the question transitions from anomaly to class of object, and the theoretical physics community will have to mobilize in response with the same urgency it applied to dark energy and the Hubble tension. A new generation of gravitational wave observatories, particularly the proposed LISA space-based interferometer and the planned Einstein telescope in Europe, may provide indirect constraints on the dark matter angular momentum scenario by measuring the gravitational wave background produced by spinning dark matter halos. If JWST ND1's halo is spinning at the rates the lensing analysis suggests, it should produce a distinctive contribution to the gravitational wave background that LISA could in principle detect. And theoretical physicists across multiple subfields, cosmologists, particle theorists, quantum gravity researchers, are beginning to include JWST ND1 as a constraint in their models. Not prominently yet, not explicitly in most cases, but quietly in the way that genuine anomalies always eventually force their way into theoretical calculations. The JWST ND1 story is not finished. It has barely begun. What you should take from this is not the specific physics, which remains contested, uncertain, and evolving. What you should take is the broader reality that the universe we live in is demonstrably stranger and more complex than our best current models describe, and that the gap between our models and reality is being revealed with increasing precision and urgency by the most powerful observatory humanity has ever built. We are at the edge of a map that has served us well. Beyond the edge, in the territory that JWST ND1 inhabits, physics is being asked to grow in ways it hasn't grown since the early 20th century. The questions are bigger. The implications are wider, the required revisions to our foundational assumptions are deeper, and the galaxy that forced this reckoning is sitting out there, 11 billion light-years away, 11 billion years old, surrounded by a spinning invisible halo that holds the secret of what happened to it, stationary, silent, and impossibly still. The universe doesn't hand us puzzles it expects us to leave unsolved. It hands us puzzles that, when solved, reveal a reality larger and stranger, and more magnificent than the one we thought we understood. JWST ND1 is one of those puzzles, and we are only at the beginning. Consider what it means to be alive at this specific moment in scientific history. Not the moment when physics was being built from scratch by Newton or Einstein. That era required the first maps. Not the mature era of the mid-20th century, when the standard model of particle physics and the Big Bang framework were being assembled. That era required filling in the details. This moment, right now, this is the moment when the best instruments ever built, operated by the best trained scientists in human history, armed with centuries of accumulated mathematical and observational knowledge, are discovering that the map is incomplete in fundamental ways. Ways that point not to small corrections, not to parameter adjustments, but to missing pages, physical processes of genuine novelty that have been operating in the universe all along and that we simply lack the eyes to see. JWST ND1 is one of those missing pages. It is not the only one. The Hubble tension is another. The early massive galaxies are another. The rapidly fading dark energy signal is another. Each one is a place where the map ends and the territory continues into unmapped ground. What gets built in the unmapped ground will be the cosmology of the next century. It will be built by people who are, right now, in classrooms and graduate seminars and postdoctoral positions, learning the current model and beginning to sense where it fails. It will be built through observations that Webb is making right now and that the ELT and Roman and Lisa will make in the years ahead. It will be built through the same combination of dogged observation and theoretical courage that has characterized every revolution in physics that preceded this one. And it will be built by people who looked at a galaxy that refuses to spin and refuse to look away. The universe is not the orderly, comprehensible structure we were taught. It is wilder, stranger, more violent, more surprising, and infinitely more interesting than any textbook captures. It is a place where galaxies can be ancient and massive and perfectly stationary, where dark matter halos can carry the angular momentum of the visible structures they surround, where the laws of physics operate at scales we have not yet fully tested, in ways we have not yet fully described, which means the story isn't over, which means there is always more to discover. If that idea excites you, if the thought of living at the frontier of human understanding, at the moment when old maps fail and new ones have to be drawn, makes you want to keep looking, keep asking, keep going further into the dark, you're in the right place. Stay curious. The universe rewards it.